So today's lecture, we're picking up from where we left off in the last class. We're still talking about steering. So how do you move? How do you compute the local motion of an object in your game? So we talked a little bit about basic motion, or I explained how to walk in a straight line, how to turn and face a target and move to the target in the previous lecture. And so today we're going to talk about chasing and evading. So motions that are a little bit more complicated than simply moving to a point or moving along a straight line. Right? In the next lecture, I guess we'll talk about, we'll also talk about flocking, and the next lecture we'll talk about obstacle avoidance. All right, so chasing and evading are the two types of motions we want to talk about today. So chasing you can think of as something moving in the world is trying to catch up to something else that's moving in the world, probably in a different direction. So you often hear these phrases predator and prey. So that's the analogy that we're going to use. Right? Your predator, in this case, you might have an enemy agent, right? Wishing to catch up to the player. Right? Now, it could be the opposite way around too, right? Your player could be trying to catch some other object. Evading is your prey is trying to avoid the predator, right? Or the agent, the AI object is trying to get away from the player in this case. Right? And so here the agent is just some AI controlled game object, right? Monster, NPC, whatever, right? It could be a car or a vehicle of some kind. And so here we've got a predator trying to chase down one or perhaps both of the two prey animals here. All right, so chasing is, evading is, simple evading is very easy to do. So it's the chasing part that's a little bit more complicated. And so if no one told you how to design a chasing algorithm, you can come up with a very simple one quite quickly. Right? So in 2D, the same works in 3D, you just have to add in another pair of directions. Right? So the absolute simplest chasing algorithm that even a first-year student could probably cook up, right, is you simply look at the position of the prey and the predator. Right? So if the prey object is to the right of the predator, you simply move the predator to the right. Right? If they're to the left, simply move the predator to the left. Right? So that takes care of moving left and right. Now, in 2D, you're going to also move up and down. So if the prey is quote unquote above the predator, right? So above on the screen, right? You move the predator upwards, right? And if the prey is below the predator, then you move the predator down, right? And that's really simple, right? It's very easy. It's extremely easy to code up, right? And this is the sort of thing that you would used to see in these, I guess in earlier games where the game was played on a grid. The game world was basically a grid of some kind, right? And so for example, here's a very, very old picture of a game that is played on a grid-like world, right? And so in this game here, every game object entity lives on a grid. So one of these colored in squares you can think of as being a grid location in the world. Right? This is still common today, right? So many games today are still grid-based. So there's nothing, and the idea is generalized to games that aren't grid-based. So there's nothing unusual, there's nothing special about the fact that this is on a grid-like world. Right? And so here, if we've got this is a troll. You can't really tell, the resolution here is really low. There is the prey, right? So the algorithm simply says, is the prey to the right? And the answer is yes, so you move right. Right? Are they above? The answer is yes, so you move up. Right? And so in this case, it's going to move up and above. Right? And so this just takes this sequence of steps, right, until it reaches here. Right? Is the prey to the left or right? The answer is no, so now you're just moving up to the prey. Right? In this case, the prey is stationary, but the exact same thing happens if the prey is moving. Right? It's just if the prey is moving, then the path obviously looks a little bit more complicated than this. So the motion this produces is, I mean, it works, right? So this will always, the predator will always catch stationary prey in this case. So that's nice. But the motion that's produced is very mechanical looking, right? This looks like something a computer would generate, right? And if you're in a non-grid-like environment, the motion's very unusual, right? Your predator basically ends up, turning to the right and moving to the right, then turning up and moving up, and then turning right and then turning right. And so they end up making this very unusual or very unnatural looking motion to chase down the prey. You can read about, there's a link here to a book in the library. It's called AI for Game Developers. And you can find this picture and a description of the algorithm in that book if you need it. The description is not very complicated, so you probably don't need it. Right. All right, so there's your basic chasing algorithm in 2D, right? Pretty straightforward. If you want something a little more natural looking, you would do something, you might consider something like line of sight chasing, right? And so this is a picture of again, stationary prey, right? There's your predator, right? The idea is that you compute the line, or the ray, I guess, from the predator to the prey, right? And that's the direction that the predator is going to take to chase down its prey. Right? So this also seems like a pretty easy, pretty simple algorithm to implement, and it is, right? Simply turn the predator so that it's facing in the direction of the prey, and then move along that line as fast as you can until you reach the prey. Okay, so now the question is what happens if the prey is moving, right? And so if the prey is moving, you don't care, right? You just assume at for every frame, you just look at what is the current position of the prey, right? What is the current, so prey, what is the current position of the predator? And you just run the simple line of sight chasing algorithm, right? So you compute, right? So you compute the line or the ray in this direction, and that's the direction that that the predator is going to move in, right? And so in that one frame, the predator moves here, right? But don't forget, the prey is also moving, or might also be moving. So in this example, in that same frame, the prey has moved from here to here, right? And now, next frame, that's the current predator location, that's the current prey location, just run the line of sight algorithm again, and away you go, right? So now, you're going to move in this direction to the prey's current position, right? Prey moves again, so you're going to repeat the process, compute the line of sight for the next frame and move in that direction, right? And so on, and so on, and so forth, right? Eventually, if the predator is fast enough, right, it will catch the prey, right, in this case, right? And this will work. The problem with this type of algorithm is that when you go to catch it doesn't actually, on the step where you catch the prey, typically what happens is you overshoot the prey, right? So you don't actually end up at the location the prey is in, you end up a little bit past it. And so what ends up happening is you end up with this wobbling motion, this oscillating motion as it tracks down the prey. Right? So how does this actually work? The math is very simple, right? So we're going to start out, here we go. So at some point in time, Q is your predator location, P is your prey location, right? How do you compute the line of sight? Well, P is just a point in the world, Q is just a point in the world. If I compute the difference, P minus Q, that gives you the vector from Q to P, right? Remember, don't compute Q minus P, that's going in the wrong direction, right? P minus Q is the vector connecting Q to P, right? And so that's your line of sight. So that's easy, right? Step 2, right? Move along the line of sight, right? So how do you move along the line of sight? The easiest way to do this is if your predator is moving with some speed s, right, over some amount of time t, right, to move it in the direction of the line of sight, you simply move it along the normalized line of sight, right? So compute the unit vector corresponding to L, right? That's just L divided by its own length, right? The normalized version of L, and that's it. Away you go. Right? And so that will eventually produce the motion here, right? It's the same thing at every step, right? Simply compute that line there, compute the normalized version of the vector, right? you know, you know how fast the predator is moving, right? You know how much time is between frames, and you know what the current position of the predator is. Therefore, you can compute the next position of the predator, right? And away you go, right? And it produces that motion there. Oops, sorry, there. Right. So that's pretty straightforward, I hope. Right. All right, now on a grid-based environment, you can use the same algorithm, but there are additional constraints when you're computing motion on a grid-based environment. Right? If you're going to force your objects to always live on a grid location, right? When you go to compute these lines of sight, you now have the problem that the line of sight must also lie on grid locations, right? So when you draw the line, or when you imagine the line connecting 2 points, so here to here, right? You want to make sure that each part of the line is a grid location, right? And so in these grid-based environments, you need to solve the problem of moving on a straight line where the line is constrained to lie on grid locations only, right? And this is the exact same problem that you have if you have what's called a raster display. So that's your modern computer display where it's made up of a grid of regularly spaced pixels, right? That's how pretty much every modern television or monitor works, right? And you now need to draw a straight line where you have a regular grid of pixels, right? And so this problem's been around a long time, since you probably haven't seen them. So there used to be something called a plotter that you would hook up to your computer. So a plotter was basically a pen that would be held in a mechanical device, and the mechanical device could move in a two-dimensional plane. And so using a plotter, you could draw straight lines on, well, it'd be easy to draw a straight line on a piece of paper or something like that. But if the steps are small enough, you can draw things that look like curves. And this is the way that you used to print computer drawings. Right. In particular, if you're an engineer and you're producing a blueprint of some kind, way back in the day, so back in the 50s, 60s, 70s, they even existed when I was a teenager. So even into the 80s and 90s, 80s anyway, they were still in use. Right. And so this problem's been around a long time. Someone figured out how to solve it in the 50s, possibly earlier, but definitely in the 50s, this guy named Bressenham figured out how to do this. Published this paper at a conference. Right? How do you draw a line on a rasterized grid? Right? So you might think this is not hard, but you can easily come up with a naive algorithm to draw a line, and your line that gets drawn is not the best looking line. Right? So notice here, you've got a line, it comes up and then it turns right and comes up and turns right and comes up and turns right. Right? Whereas with Bressenham's algorithm, you never have lines that look like this, right? And you get a nicer looking line. Modern versions of this algorithm also do what's called anti-aliasing, right? So instead of looking like this jagged appearance, modern versions of the algorithm can compute an intermediate color, somewhere between white and gray for this pixel, and this pixel, and the pixels around the line. So that provides the illusion of having a smoother shaded line, right? If you've ever used any drawing software and drawn a line and then zoomed in, right, you'll notice that the line, assuming you've got anti-aliasing turned on, right, the line that gets drawn is not all one solid color, right? It's a blend of the color of the line and the background. So that's the anti-aliasing algorithm at work. You might learn a little bit about anti-aliasing in graphics. Probably not, but you might. Okay, so how does Bressenham's algorithm work? So the picture I'm going to show you here only works if the line that you're drawing has a slope between 0 and 1. Right? So in other words, So the pictures I'm showing you only work for lines in this region here. Right, or lines whose slope would be between 0 and 1, right? So their angle is between 0 and 45 degrees, right? The line doesn't have to be in this quadrant here. It could be anywhere, but the slope of the line is between 0 and 45 degrees, right? And so the idea is here, I know where the starting location of the line is, and I know where the ending location of the line is. And these are integer coordinates because you're on a regular grid, right? And I would like to know, how do I fill in the pixels between those two lines to get an quote-unquote ideal line, right? And so the idea here is that you can draw this line as long as the slope is between 0 and 1, right, by stepping along the x-axis and computing which pixel to turn on, right? So you have a little loop for x equals x0 to x1, right? At the start of the loop, you can color in the endpoint, the start point and the end point, right? So at the start, I know that the line, I'm going to turn on this pixel to represent the line, right? Next iteration of the loop, you're going to increment x by 1. So you're going to go to the next row, right? And if the slope of the line is between 0 and 1, you've only got one question to answer, right? The question is which pixel do I shade blue, right? Do I shade the lower one blue, or do I shade the upper one blue, right? This picture here, it's not obvious which one you would do, but it turns out you would probably shade the bottom one blue. So I'm going to do that, right? Next iteration of the loop, increment x by 1, right? So now in this row, right, again, if the slope is between 0 and 1, either this pixel gets turned on or this pixel gets turned on, right? I don't care about this one or this one because the slope of the line is between 0 and 1. So next iteration of the loop, the algorithm asks, which one do I turn on, right? In this case, it's a little bit more obvious. You're going to turn on that pixel there, right? So we do that. Next iteration of the loop, add 1 to x, and the question is, which one of these two pixels do I turn on, right? And so on, right? And so on until you draw your line, right? So the only interesting thing here is the question, which pixel do I turn on, right? And it turns out there's a very nice mathematical answer to this, right? I don't care if you know the details, but I'll just quickly sketch them out for you right now, right? Just in case any of you are actually interested in how this works. Right, so you remember what the slope with the equation of a line is, right? It's y mx plus b. Right, m is the slope of the line, b is the y-intercept, right? So they're constants in this case because the line in this case is constant, right? How do I compute the slope of my line? It's just the rise over the run, right? So, okay, so if the line the slope is always between 0 and 1, then I can easily compute the rise, right? The rise is just the difference between these 2 points, right? So it's y1 minus y0. Right? And what's the run? Well, the run is just the difference, the horizontal difference, right? So that's x1 minus x0. X plus b. Right? I'm going to write this so dy, and dx must be like that, right? Get rid of the fraction, so multiply both sides by dx. Like that, right? Take the y over to the other side, and you get 0 equals d1 minus dxy plus dxb. Right, and that becomes the equation of your line, right? So all that equation says is that the points that lie on the line have coordinates x and y such that the sum on the right-hand side, or the part on the right-hand side, is equal to 0, right? Now it turns out if you're above the line, right? So suppose you're on this point here, right? If you plug in that value of x and y into that equation there, you get a value who's negative, right? So any point above the line is negative, any point below the line is positive, right? This part here is greater than 0, right? And so when you go to decide which one of these do I turn on, right? I know the coordinate of that point, I know the coordinate of that point. So you can go halfway in between, right? And you compute that equation at the point halfway in between. If the result is negative, then you know that point is too high, and so you turn on this pixel. If this point is positive, then you know you're too low, so you turn on that pixel, right? And that's the basic idea of how Bressenham's algorithm works, right? It computes the error between the line location and a pixel location, and it picks the pixel which produces the smallest error. Right? For those of you who are thinking about grad school, this is what you used to have to do as part of your PhD. Right? Obviously, the problems you solve nowadays are much harder. All right, so the idea there only works if the slope is between 0 and 1. Right? You might ask, well, why does it only work if it's between 0 and 1? Right? And so the answer is because here I'm stepping the x coordinate by 1 every time. Right? If the line is more upright, then what you want to do is you want to step the y coordinate by 1 every time. Right? If the line is upright and pointing to the left, right, you want to step the y coordinate up by 1, but you also want to move to the left. Right? And so it turns out that there are 8 separate cases for what exactly it is you need to do. Right? So in other words, you need to handle, oh, I erased the picture. And so you need to consider lines whose slopes fall into the 8 different octants. Right? But it turns out there's an easy way to handle lines of any slope. Right? And the algorithm, if you want to look at it, it's in the Wikipedia article that I linked. People have come along and made extensions to this algorithm. So people know you can extend the algorithm to ideally draw a circle, any other curve that you can specify mathematically. Right? If your line has a different thickness than 1, you can, there are versions that can handle that. Right? And there are versions that can handle anti-aliasing and so on and so on and so forth. Right? I don't think anybody's still making variations of this algorithm. Right? So the basic algorithm is known. You can look it up. It's relatively easy to implement. Right? And so if you're going to do, here we go. If you're going to do line of sight chasing on a grid-like world, somewhere in your game engine, somewhere in your code is going to be an implementation of Bressenham's algorithm. And so line of sight chasing, instead of moving left and right and then moving up, right, you're just going to move into move in a more or less straight line towards the prey. Okay, and so if you've been paying attention and you looked at the previous pictures here, right, where we're doing line of sight chasing to catch the prey, the obvious question to ask is, well, instead of moving toward the prey's current location, why don't we try to anticipate where the prey is moving and move in that direction? Right? I don't know if any of you have seen this, or if any of you are interested in Australian rules football. Where is this slide that has this? Here. This showed up on Reddit last week sometime. Okay, so there's your prey. You're going to try to catch him, right? There's your predator, catches him just before the goal line. Okay, so that's the idea of this intercepting chase, right? You want to anticipate where is the prey moving to, right? And instead of moving towards the prey's current location, move towards the prey's future location, right? So this kind of chase algorithm will let a slower predator possibly catch a faster prey object, right? So the reason you can do this, so in the video I just showed you, the distance that the predator is moving is shorter than the distance that the prey is moving in this case, because he's coming at the prey in a diagonal direction. So instead of moving toward the prey's current location, you want to guess where is the prey moving to, right? And so here you've got a prey object that's moving in this direction, right? A more intelligent predator, instead of moving this way, right, and sort of following a path like this to catch the prey, right, might just simply move in this direction to intercept the prey along its future path. Okay, so now the question is well, how do you actually guess or anticipate what the future position of your prey will be, right? Because you don't know what the prey is going to do, right? It might change direction, it might stop, right? So it might change its speed or something else, right? And so all that you can do is work with the information that you currently have, and that is you know what direction the prey is moving in. You can guess at how fast it's moving at. If it's a video game, you know how fast it's moving at, right? So your predator might have perfect information, right? And so you can, if you assume that the prey moves at the same speed in the current direction it's moving in, you can guess where it will be in the future, right? It's easy. You know the direction it's moving in. You know how fast it's moving in, right? You can simply multiply its speed by the time and the the direction that it's moving in, and that will tell you where it will be in the future, right? Okay. Now the question is how far into the future are you going to guess, right? And so that's part of the problem that you have to solve. If you guess too far in the future, then you're going to assume the prey has gone much further than it probably has, than it actually has, right? And so you'll end up overshooting the prey's location. If you guess too near in the future, the prey will have gone past that point and you will undershoot the prey, right? So you have to guess somewhere. You'll have to guess somehow at it. You have to guess some amount of time at which to anticipate the prey's future location. So the way you do that, or one way that you can do that, right? If you know how fast the predator can move, so you have its top speed, right? You can compute the distance, the current distance between the prey and predator, right? So P is the prey's location, Q is the predator's location, right? What is the distance between them? Well, take P minus Q and take its length, right? P minus Q is just a vector. Take the length of the vector. That's the distance between the 2 points, right? If you know the top speed and you know the distance that needs to be traveled, right, you can guess at a closing distance, right? The closing distance is the closing time, the amount of time it takes to travel that distance at that speed is simply the distance divided by the speed, right? And so that gives you an amount of time at which you can guess into the future, right? And so that's easy. You just take t-close, right? You multiply it by the prey's velocity. If you have the prey's speed and direction, then that becomes s times d instead of v, right? But same thing, right? Add it to the prey's current location, and you now have a guess as to where the prey will be in the future, right? And now you simply use your line of sight chase with p prime instead of with p, right? So you do line of chase to the anticipated location of the prey instead of the current location of the prey. Right? The problem with this algorithm here is that when you guess this time, right, if that time is very large, then your assumption that the prey is going to continue moving in a straight line at its current speed is probably not very good, right? So in other words, your guess is probably going to be pretty bad. So if the time turns out to be large, what you typically do is you pick a smaller time. So in other words, in your algorithm, normally you set a maximum time on t-close. If t-close is greater than the maximum time, you use your maximum time value instead, right? And that would be the way that you would handle that. Right? And so there's how you perform intercepting chase. Right? And this is probably this produces pretty realistic, reasonably good looking paths for your chase. Right? There's still a few problems. So when you actually close on the prey, again, typically what happens is you will overshoot the prey's location and you end up with this oscillating motion as you close in on the prey. Okay, evading is much simpler than chasing, right? So if that's your predator and that's your prey, right? In this case, this is your, so this is the player, right? That is an object under control of the computer, so it has some sort of AI in it, right? If this thing is the prey, then it's pretty easy to figure out how should I move away from the predator, right? All you do is you compute that vector, right? The line of sight vector between the player and the target, right? And you simply move the target in the direction C in this case, right? You simply move away in the direction that the player is moving in, right? And that's the simplest evading algorithm. Okay, so there's lots and lots and lots of other steering behaviors that you might want to put into your game, right? the list is more or less endless, right? Like you can come up with lots and lots and lots of different scenarios where you want to steer a predator towards the prey in a certain way, right? So for example, position matching. So you might want to match the position of the predator. You might want the predator to match the position of the prey, right? But that's basically like moving to a waypoint. So that's pretty easy. So if you have waypoint motion already in your already programmed, you've already got that kind of matching. Yeah.
For line of sight chasing,
Yeah.
what's the solution to ensure that the AI stops its behavior if the player like goes behind a wall or something and they're still in like their zone of chase?
Okay, so that kind of that problem doesn't fall into what we're talking about now, right? So we're talking, right? So when you have to take into consider other factors, right? That goes up to the next level of your AI, right? So we're going to get to that in subsequent lectures. So for next class, we're going to talk about avoiding obstacles, right? What you're talking about is if you lose sight of the prey, right? You now have to switch the behavior of your. You now have to switch the behavior of the predator, right? Okay, so that now introduces the problem of what state is your predator in, right? So what is it doing? Is it still chasing? Is it evading? Is it doing something else, right? And so that falls into the next level of AI, right? Yes. Yeah.
Following that same line of sight.
Boop, here. Yeah.
So wouldn't that be faster for the predator? The target's going to still be on the same line.
Sorry. No, so your question. The answer is so no. So look. So if you're trying to escape something, right, that's chasing you, right, then the fastest way to get away from the thing that's chasing you is to move in the same direction that it's chasing you in, right?
I guess in that case, you just have to consider the other movement speeds.
Yeah. So if the predator is slower than the prey is guaranteed to get away, right?
Not like zigzag.
Yeah. So zigzagging again, that's going to be a different type of steering behavior. But yeah, so that would be a completely other form of evasion, right? Yeah, and so you'd have to program or figure out how would you program that into your game. So there's position matching, so that's like moving to a waypoint. There's velocity matching, so that's when your predator, quote unquote predator, right? The terms predator and prey don't always mean predator and prey, right? It's just, so for velocity matching, you want your two objects to be moving in the same direction at the same speed, right? Now this isn't necessarily a chase scenario. So for example, if you have a marching band or some sort of formation, right, you might want everything to be moving in the same direction at the same speed, right? It's a chase. It is a chasing problem, right? But there's no real predator or prey, right? You just want everything to be moving in the same direction at the same time. So that's called velocity matching. That's easy to do too, right? You have a bunch of objects, you want them all to go in the same direction, you just make them all point in the same direction, right? So turn, right? Set their orientation so that they're all pointing in the same direction, and then move them forward in the direction that they're facing in. So typically in this velocity matching problems, there's a leader, right? And then there are its followers. Following is similar to velocity matching, right? So in following, you would like your predator to close to within a specified distance of the target, right? And then perform velocity matching, right? So for example, you can imagine if you want to trail somebody, if you're a spy, I guess, trying to trail somebody, or a private investigator trying to trail somebody, right? You want to close to within a certain distance to the person you're following, and then just follow the same path that they're taking, right? If they stop, you want to stop, right? If they turn, you want to turn where they turned. Right? arriving is like chasing, but the problem with chasing is that, especially if you have a predator that's much faster than the prey, is that the predator often overshoots the prey, right? And so the way to solve that is to start to slow down or change the speed of the predator as it gets closer to the prey, right? So as you get closer and closer to the prey, you set your velocity closer and closer, your speed, sorry, closer and closer to that of the prey. Right, and that prevents this overshooting problem where you end up running past the prey and then have to adjust your path so that you go back to the prey. Right, and you can keep on going on and 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 on, right? So chapter 3 of this book here, which is in the library, here, there, it's AI for games. Can I get a bigger picture? Right, so this is AI for games. This is the most recent version of AI for games. It's this big fat book like this, and there's an entire chapter of steering algorithms that you can look at there if you're interested in that. Okay, so we could go on and on and on and on, but rather than going on and on and on and on, we'll look at a slightly different but related topic, right? And so your reading for this week is the original flocking paper. And so in flocking is a movement behavior of a group of similar objects, right? And so the paper that you're going to be reading talks about these things called boids, right? A boid is sort of a play on word of birds, right? And so the algorithm that was designed there was meant to provide a simulation of the behavior of flocks of animals, right? So a flock of birds, herd of animals, or something similar. Right? So the idea here is that you've got a multiple similar objects that are moving together more or less as one unit, right? But they're not all moving exactly the same, right? Because that's not going to look natural, or it'll look, it will look, well, sorry, it's not going to look like natural animal behavior, right? So you want some sort of variation in their behavior as well, right? So the animals are roughly moving in the same direction at roughly the same speed, but there's some variation as well, right? If everything's moving in the same direction at the same speed, that's like a marching band or something like that, right? Okay, so this link here takes you to a video which Stanley and Stella. And so I guess we'll watch part of this. And as it's playing, I'll describe. Okay, and I'll tell you about symbolics in just a second. Right, and so this was the original Boyd's video that was shown at the conference that the paper you're about to read was published at. Right. Of course, this was a long time ago, right? So this was in the early 80s. So the graphics are not impressive by today's standards, right? But notice already you've got a bunch of these fish, right? So these fish are moving around and they're programmed with this Boyd's algorithm, right? So notice that there's a group of fish. They seem to be moving together, right? But notice that they're not all moving with the same motion, right? Oh, these are birds now, right? They appear to be moving as one large group, but individually they're all moving in a different direction. This was groundbreaking at the time, by the way. Right? And you can do the same thing with fish. And in fact, many of the screensavers and simulations that you see where there's a whole bunch of fish, they all use a variation of this Boyd's algorithm. Okay, that's enough of this. These are not the most exciting graphics in the world. But take my word for it. This was groundbreaking at the time. Right? So the company that developed this was a company called Symbolics, right? So Symbolics no longer exists. They went bankrupt. Symbolics was known for producing a special type of computer, and that computer used this language called Lisp as its programming language. Did they show you Lisp in 360? Yes? No? Okay. So that's a little surprising, actually. Did you take 360? They didn't show you? Okay, so that's shocking. Lisp is one of the very, very important programming languages in computing science. No one uses it anymore, But historically, it's extremely important. So they made these computers that basically ran Lisp. But they did a whole bunch of other things as well. So this is one privately held company. There's a whole whack of contributions that they made to computing. Right? They made one of the earliest object-oriented programming languages in Lisp, right, as a variation of Lisp. Right? Garbage collection. So your languages like Python and Java, they all use garbage collection to remove unused objects. Symbolics is one of the first companies that actually put this into practice. Again in Lisp, unfortunately. Right? They were a company that introduced one of the first object relational databases. Right? That's kind of a big deal. Right? They made their own microprocessors. This is one of the reasons why they went out of business. Right? Eventually, Intel came along and killed everybody. Right? So Intel managed to make a cheap CPU, and that basically killed a whole bunch of computer manufacturers. Right? But the thing that I just showed you there, their graphics division, which was basically one guy by the name of Craig Reynolds, wasn't a large group. There's a few people, right? He made up this Boyd's algorithm. Right? And so that got published in 1987. You're going to read the paper. That video I just showed you was a paper, was the video that was shown at the conference. He went on to win an Academy Award for his contributions for computer graphics into movies. Right? So it's kind of crazy what this one company actually did. They did a bunch of other stuff too, and then they went out of business. So computer graphics is filled with companies that followed a similar path, right? So there used to be a company called Silicon Graphics. Anybody, have you heard of SGI? Has anybody heard of SGI? Okay, so I did my PhD here at Queen's with Randy Ellis. So my PhD was in computer-aided surgery. So we had a system, we had a computer that we drag into the operating room that would show the surgeon where their surgical instruments were with relations to relative to a preoperative surgical plan. And so this was all computer graphics, and it ran on an SGI, or Silicon Graphics workstation. And so SGI was one of the first companies to come along and produce workstations dedicated to computer graphics. Right? There were a bunch of companies around that made workstations, that made Unix-based workstations. Right? So there used to be a whole bunch of these things. They all made their own CPUs. Right? They all had their own version of Unix. Right? And then Linux and Intel came along, and they all went out of business. Right? They couldn't compete anymore. But SGI, 8 consecutive years, the films that won the Academy Award for visual effects, they were all done on SGI machines. Right? Not single machines. We're talking like hundreds or thousands of SGI machines. Each one costing somewhere between $10,000 and $50,000. Right? So all of Pixar's early stuff is all SGI. It's all done on SGI machines. Right? Jurassic Park, SGI. Twister, SGI. Right? And it goes on and on and on this list. Right? Where's SGI now? They're gone. Right? One of the big problems was, anybody use Maya? The 3D software Maya? Okay, so Maya used to only run on Unix workstations. It was first developed for engineering applications. It would only run on Unix workstations. So it used to run on SGI machines. Right? Eventually, Autodesk got around to moving it to Linux-based machines, and SGI's market disappeared. Right? Why pay $10,000 for a Unix license when you get Linux for free? So there's a whole bunch of these. There's a whole bunch of graphics companies that had very important contributions that are now gone. Okay, flocking. So how does flocking work? You're going to read about this, so I'm just going to very quickly take you through it. It turns out to be really simple to do. Right? And so the idea is that every object in your flock is trying to choose its direction based on 3 different priorities. Right? So the number 1 priority is this thing called separation. Right? An object should not collide with another object in the flock. Right? This behavior has the highest priority for obvious reasons. Right? You don't want your, well, visually you don't care if 2 things crash into one another, but if you're trying to simulate an actual flock, then you don't want 2 things to crash into one another. Right? So whatever happens, the objects are going to try to steer themselves so that they don't run into another instance of themselves. Right? Now, notice the problem here. Right? The problem here is that so for the object that's in green, right, it needs to be able to compute what are my nearby objects, right? If you have 1,000 objects in the flock, right, that becomes a fairly expensive computational problem, right? You have to figure out, okay, so what are the nearby objects, right? What is involved in doing that? Well, the review questions ask you about that. Okay, so you're gonna make sure that you don't crash into something else, right? And so once you've taken care of that, you now need to decide, all right, well, so what direction is it gonna move in? And so the answer here is that, well, we kind of want to move in, we want all of the objects to be roughly moving in the same direction. So let's steer towards, or steer in this average direction of all the other objects in the flock, right? So they're all moving in a slightly different direction, slightly different directions, but if you average all the directions, that gives you the overall direction that you want to move in. And so all the objects will try to steer in that direction. Right? And then finally, you want to, oh, sorry, that's the cohesion. You want them all to stay together. I think I got them mixed up. So alignment means steer in roughly the same direction. And then where are you headed? Well, you want to move in the direction that is pointing into the middle of the flock. Right? So you want to try to steer towards the average position of the objects in the flock. Right? In this priority. Right? And so if you do that, you end up with the video that I just showed you. And in real life, this actually does sort of happen. Can I play this? Okay, so I have the video separately. So this does in fact happen, or something similar to this happens in the real world. This is a flock of starlings, so the green and black birds that you might see flying around. And this is called a murmuration of starlings, right? And you can see there's this big flock that occasionally splits into two pieces and then rejoins. And notice that they're all sort of moving in the same direction, right? That tail was about to splits off, right? And there you see a tail, another group splitting in, joining the main flock, and you end up with this sort of motion here, right? And so this is the sort of motion that you can reproduce using a flocking type algorithm. Okay. Oh, we're out of time, so that's perfect. So that's the end of that lecture. The paper is, so I recommend you read the HTML version of the paper rather than the original version. The original version is scanned. The paper is so old